Okay, we started out by saying that the first part of this course was going to be on differential equations, and in fact mainly on initial value problems. And you now have everything that you need in order to solve initial value problems in which the differential equation is a linear differential equation with constant coefficients. The idea is simply to take the Laplace transforms of all of the terms in the equation. That turns it into an algebraic equation in the Laplace variable s. You solve that algebraic equation, and then you transform the result back to the time domain. Let's take a look at a simple example from the notes just to see how that works. So you have all of the ingredients given that you know how to compute Laplace transforms and you know how to invert Laplace transforms. So if, for instance, you have this differential equation, y dot, or dy by dt, plus y equals t plus e to the t, y of 0 minus equals 1. So we're interested in solving forward, if you like, from time t equals 0. So we'll use the unilateral Laplace transform, and we'll simply take the Laplace transform of every term in this equation. So as I said in the previous lecture, we could have done this as soon as we'd covered the differentiation property, because the differentiation property lets us handle the first term in this equation. According to property 6, differentiation, the Laplace transform of dy by dt is s times the Laplace transform of y itself minus y at 0 minus. And in fact, our initial condition gives us the value of that y of 0 minus. The Laplace transform of y itself is just y of s, which we're going to solve for. Then taking the Laplace transforms of the sort of forcing terms on the right-hand side, we get 1 over s squared for the ramp and 1 over s minus 1 for the exponential. Again, the idea is that we're solving for, say, t greater than or equal to 0. So we're using the unilateral Laplace transform for that reason. Okay, well, now we've got an equation, an algebraic equation in y of s. In fact, we know that this y of 0 minus is 1, applying our initial condition. So we can simply solve this. Doing so, we get an expression for y of s, which is 1 over s plus 1 plus 1 over s squared times s plus 1 plus 1 over s plus 1 times s minus 1. Maybe I should say a little bit more about this. So if I back up a step, on the left-hand side we get s plus 1 times y of s. And on the right-hand side, everything is known. So we get 1 plus 1 over s squared plus 1 over s minus 1. This 1 here just results from our initial condition, y of 0 minus is equal to 1. And the other terms on the right-hand side are just the transform of the forcing function. This s plus 1, of course, comes from the terms in y of s. And this particular polynomial that multiplies y of s is what is called, at least in the classical approach to differential equations, the characteristic polynomial. We would have got this no matter what forcing term we had had on the right-hand side of the equation. This just arises because of the specific linear combination of y and its derivatives that appears in the equation. And as we'll see when we get to systems and signals, this characteristic polynomial essentially captures the intrinsic dynamics of the system itself, which are sort of independent of any forcing function that you might apply. So I just mentioned that terminology. S plus 1 is the so-called characteristic polynomial. And if we divide both sides of the equations by s plus 1, we come up with the previous equation, where we see an s plus 1 in the denominator of every term on the right-hand side. That, in a sense, shows how the intrinsic dynamics of a system modeled by this equation show up. The other terms in the denominators have to do with the form of the forcing function. So we'll come back to this notion of a characteristic polynomial later. For now, if we just turn the crank, we can find y of t easily, the unique y of t that satisfies our initial value problem. Of course, we're going to do this inversion by taking partial fractions decompositions of the terms on the right-hand side. I won't go through the details, but if you do that, you end up with y of s equals 3/2 over s plus 1 plus 1 over s squared minus 1 over s plus 1/2 over s minus 1. This first term has in its denominator the characteristic polynomial. The other denominators essentially arise from the forcing function. So y of t we can now get by inverting these simple transforms into which we've decomposed the expression for y of s. This first one is, of course, the transform of an exponential e to the minus t. I won't bother putting in the unit steps to make it clear that we're talking about one-sided functions. I'll just say 3/2 e to the minus t. This second term is the transform of a unit ramp, so that gives us a t. The next term is the transform of a unit step multiplied by minus 1, so we get minus 1. And finally, we have 1/2 times a growing exponential, which corresponds to the growing exponential in our forcing term. So in a sense, this decaying exponential, the first exponential that we found, the decaying one, that stems from the intrinsic dynamics of a system modeled by this equation. And it comes essentially from the root of the characteristic polynomial at minus 1. These are the so-called eigenvalues, but we'll cover this when we look at systems and signals. So there it is. That's our solution of the initial value problem. When we use the Laplace transform, it's quite simple to solve these problems. And indeed, this approach is quite a standard one. If you pick up an introductory textbook on differential equations, you will find this approach. It may not be presented until chapter 7 or something like that. Normally, people will present what you might call a more classical approach to the solution of these linear differential equations with constant coefficients. But I don't think that classical approach really buys you anything. It's a sort of old-fashioned bag of tricks approach. A bit like when you integrate, you have to use a collection of certain tricks which may or may not help for a given integral. And there's a similar kind of bag of tricks approach to the solution of linear differential equations with constant coefficients. But this approach based on the Laplace transform is much more general and powerful and systematic, I would say. Excuse me. So you now know, essentially, how to solve linear differential equations with constant coefficients and the associated initial value problems. Just take the Laplace transform of every term in the equation, plug in the values of any initial conditions that you're given, and then invert the transform to get the solution of the equation. This assumes that the driving function, what we've been calling f of t in our standard expression for a linear differential equation with constant coefficients, is given. And that's the usual setup, that's the usual problem formulation in mathematics. And that's the usual sort of thing that, for instance, natural scientists are interested in. A physicist, for instance, might write down a differential equation that describes the dynamics of a system he's interested in analyzing, together with the appropriate forcing function. So if it's a problem in mechanics, the forcing function might give the forces applied to the system as a function of time. And then he would solve an initial value problem, say, in order to see how his system is going to evolve in time. That's because natural scientists are essentially mainly interested in analysis. Okay? They assume that the equation that models the system is a given, and so is the forcing function that's going to be applied to it. But in engineering, we're typically interested in what you might call an inverse of that problem. We might have some idea of what we want the response of a system y of t to look like, and we might need to find a forcing function f of t that will give us such a response. In control, when you're controlling a system, that, roughly speaking, in the very broadest sense of control, is the sort of thing that you're interested in doing. So we're more interested in what you might call synthesis problems, which are harder problems. And that's why we've developed this systems and signals approach, which essentially, instead of just letting you solve an initial value problem for a given forcing function, gives you a better idea of the relationship between a whole class of possible forcing functions and the corresponding responses. So we're going to study the relationships between forcing functions and responses by taking a systems and signals approach. Before we do that, let me just say a little bit more about this approach to solving initial value problems. We started out by saying that a linear ODE with constant coefficients is something of this form, where we have this y of t function, and we have terms that are either y of t or or derivatives of y of t multiplied by constant coefficients. We could write them on one side of the equation if you like. And then we have similar terms involving what we've been calling a forcing function, which for natural scientists might be a given. But again, in engineering, often we need to find an f of t that gives us a y of t with certain desirable properties. And that's why we need to go beyond the techniques that we've seen so far. Now, by recalling this equation, I just wanted to say that provided that m is less than or equal to n, and as it has been in the way we've been writing the equations, this leading coefficient here in front of the nth order derivative is unity. In that case, then these same techniques apply when y and f are vector valued and the coefficients are matrices. So if the leading coefficient is the identity matrix, and y and f are vector valued and the coefficients are matrices, then our techniques extend to this case. So in other words, you can also use this approach to solve coupled systems of linear ODEs, and that's another big advantage over the classical approach. So provided m is less than or equal to n, and an equals, let's say, I, the identity matrix, our Laplace transform techniques extend to coupled systems of equations. So for instance, where the functions y and f are vector valued, and the coefficients, the constant coefficients, say ai and bj, are constant matrices. So that's another big advantage of this approach. Under those conditions, it extends straightforwardly to the case where y and f are vector valued, in other words, the case of coupled systems of equations. So in the signals and systems framework that we're going to go on to look at, this means that the techniques extend to so-called multivariable systems. We're going to restrict attention essentially to single input, single output systems rather than multivariable systems. But all of our techniques will extend to this so-called multivariable case. I think we'll leave it there for this week. Before we go on to signals and systems, there's one other topic we're going to cover, which is that of a generalized function known as the Dirac delta function, or the unit impulse function. But we can leave that for next week. So what we've done for this in this week's lectures is to complete our list of the properties of the Laplace transform by looking at the initial value theorem and the final value theorem. In order to talk about the final value theorem, we introduced rational functions, or at least the definition of rational functions, and some terminology concerning rational functions having to do with properness, strict properness, poles and zeros. And then we observed that the tools that we've developed so far let us solve these initial value problems involving linear constant coefficient differential equations. And that's true, as I've just said, even if our functions are vector valued under a mild assumption that that leading coefficient is the identity matrix. So let's leave it there for this week.